Hey everybody, Mr. Judson here. So we have two things to talk about today. One thing is this idea of the one-to-one property. The second thing we want to look at is if you invest money, what are some simple formulas that we could use to determine how much money we'll have at the end of an investment. Okay? So let's start with the one-to-one property. What this says is that if a to the n power is equal to a to the m power. So by using the same variable for these bases, that means that the bases have to be the same for this to be true. Okay? If a to the n equals a to the m, then n has to equal m. If those bases are the same, there's no way they can be equal unless the exponents are the same. Right? That's what they're saying here. And so maybe they have some expressions in here that we would set equal to each other and then try and solve and figure that out. Likewise, if a to the n power equals b to the n power, so if the exponents are equal, then the only way the two expressions can be equal is if the bases are. So then a has to equal b. Okay, that's the one-to-one property. There's a lot of different forms that this comes in, but what we're really saying is if two things are equal to each other and there's only a slight difference, in this case the exponents, well then the exponents have to be equal. If the only difference here is that the bases are different but the exponents are the same, well then the only way they're equal is if the bases are the same. Okay? So that's what we want to start with. So let's take a look at a problem here. All right, so if I take a look at this, this is 16 to the 1 power, so my bases are not equal to each other. So how would I solve this equation? Well, my first thought is, could I write 16 as 2 raised to some exponent? And if I can, well then I could go ahead and do this problem. So I would look at this and say 2 to the x minus 3 is equal to, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. So that would be 2 to the 4th power. Okay, so a lot of times we say, you know, if our problem doesn't look the way that we want it to look, we got to make it look that way, right? And so that's what I've done. I've just made it look like this. So if those two bases are the same and these are equal to each other, the only way that happens is if those exponents are equal. So x minus 3 has to equal 4. If I move that over and add 3, I get x equals 7. There it is. So if I want to just double check my answer now, I could go back here and say, all right, let's put a 7 in here. 7 minus 3 is 4. 2 to the 4th power is, 16, so that works. Okay, let's try another one. All right, so now I've got e to the 2x minus 1 equals e to the 4th. You guys go ahead and solve it. All right, so again, bases are equal to each other, so the only way these two expressions are equal is those exponents have to be equal. So 2x minus 1 equals 4. If I add 1 to the other side, I get 2x equals 5. And then divide by 2, I get x equals either 5 halves or 2.5. I don't care how we write that. Either way is fine. All right, so that wasn't too bad. Let's try another one. All right, you guys go ahead and try this one. All right, so if I was going to work through this, here my base is 1/5, here it's 125. I know that's 5 to the 3rd power, right? 5 times 5 times 5. So I could at least write that in here, but that doesn't make my bases equal. Okay, 1/5 is not equal to 5. So what I'm going to do is, and this is where it's probably really important to remember the properties of exponents. One of the properties is if you've got a fraction raised to an exponent, both the numerator and the denominator get raised to that. So this would be 1 raised to the x plus 1 over 5 raised to the x plus 1 equals 5 to the third power. Well, I know 1 raised to any exponent is just 1, right? 1 times 1 times 1 times 1. Whatever x is, I don't care. I'm just going to keep on multiplying 1s, and so I'm just going to get 1. So I'm going to write that as 1 over 5 to the x plus 1 equals 5 to the third power. And so now we want to think about this property. If you have x raised to a negative exponent, that means 1 over x to the positive exponent. I always say that negative exponents mean that you move this to the other side of the fraction bar and you make that exponent positive. Well, this looks kind of like this side. So what I want to do is I want to go from this back to here. So it means if I make that exponent negative, I could write it this way. 5 to the negative x plus 1 equals 5 to the third power. And now I have the one-to-one property. The bases have to be the same to be able to say the exponents are equal to each other. Okay, so at this point I'll go ahead and distribute that negative sign. I'll get negative x minus 1 equals 3. To get my x positive, I'm going to move it over here. I'll bring that 3 back over here and subtract it, so this will be a negative 4. And there it is. There's my answer. Now, could I check that? Sure. I can go back and say, let's plug that negative 4 in right here. Negative 4 plus 1, that's a negative 3. So we'll just do this off to the side. 1/5 raised to the negative third power means 1 to the negative 3 over 5 to the negative 3. 1 raised to anything is just 1. If I take this 5, remember a negative exponent means move it to the other side of the fraction bar. So if it's in the denominator, I want to move it back up to the numerator and make it positive. So this is just going to be 1 times 1 times 1. If you want to, you can say let's move it down below. You can really do this. 5 to the third power over 1 to the third power. 1 times 1 times 1 is 1, so it's really just 5 to the third power. And what's 5 to the third power? 125. That works. Okay, so I was just able to check that answer. All right. So that's one thing we have for today. The other thing we have for today is this idea of putting money into an investment and then trying to see how much it's worth at a later point in time. Okay? So there's 2 ways that things can happen. First of all, let's make sure we understand this word. Interest is compounded. The word compounded means how many times do they actually pay interest on your account. Some banks will pay interest once a month, so that's 12 times a year. Okay? Interest is compounded n times per year. If they pay interest monthly, 12 times a year. If a bank says, well, we compound interest weekly, okay, well, that's 52 times a year. Sometimes people would think, oh, you should go with that because you're getting paid 52 times instead of 12. But you're getting paid a smaller amount. So it doesn't really work that way. You might make more money, but it's not a lot. It's like pennies. Okay? Some people might just say we compound quarterly. That would be 4 times a year. Every 3 months is when they pay interest. Okay? And they do that because what they don't want you to do is to put money into your account and then take it right back out again. They want you to put it there and leave it there so that it can earn some interest. All right, so if interest is compounded, this is just abbreviation for interest. Interest is money that the bank pays you when you leave it in the bank. So I don't know if you guys know how this works, but when you put money into a savings account, what the bank does is they turn around and take your money and loan it to somebody else. And they charge them a higher interest rate, and then they pay you a little bit of interest so that you get some of it. Now, the problem is in a bank that the interest rate is so low. I mean, like it's so low, it's ridiculous. It's like 0.003%. I think I got 21 cents last time I checked. Pointless. It makes no difference. I could care less about 21 cents. I want a bank that's going to pay me 8%. Well, no bank is going to pay you that. So then you go to things like stocks and bonds and mutual funds. But you can find it. It's out there if you know where to look, all right? Or 10%. I think there's investments that probably paid 30% this year. What about Pfizer? You know, coming up with a vaccine. Oh, if you would have bought stock in Pfizer at the beginning of COVID, you would have done quite well. You would have done well, okay? So, interest is compounded a certain number of times per year. The formula that we want for that is this. A equals P times 1 plus R over N raised to the NT. And we'll talk about what all these variables mean here in a second. Some banks will say, well, we pay interest, or we compound interest continuously, non-stop. Sounds like a lot of money, but it's really not that much different. It's a little bit higher than this formula, okay? But the formula looks different. A equals P times E raised to the RT. So remember that number E? 2.718. I call this the Pert Formula, and I always call it that because there used to be a thing called Pert shampoo, and I think we used it at our house when I was growing up. I don't see it anymore, but that's what helped me remember that formula. E is used anytime things change continuously. It doesn't have to be money. It can be population. You know, the population is growing continuously. It can be an animal population, right? So anything that changes continuously, we need to use this formula. All right, so here's what this stuff stands for. So P equals the one-time deposit. So if I want to deposit $1,000 into my account, I'm going to put $1,000 here or $1,000 here. Okay? I'm not going to keep on putting money in. I get to do it one time. Right? That's what these formulas are for, one time. R is the interest rate. So if the interest rate is 7%, that means R equals 0.07. You got to take that percentage and convert it to a decimal number. Okay? So this R right here is the same as that R right here. These P values are the same thing. N equals the number of times interest is compounded. Okay, so compounded means the number of times interest is paid. All right, what do we have left here? We've got T. T equals time in years. All right, notice how there's no N over here? That's because interest is being compounded continuously, and the number E takes care of that for us. Okay, so T is our time in years. And then A equals the ending amount. Okay, how much money am I going to have at the end of so many years? A is going to tell us what that is. All right, so here's a sample problem. So I want to, let's see, I'm on number 4, I think. I want to invest, let's say $5,000 at 8% compounded monthly for, these books are always, or these problems are always so boring in our book because they don't leave it there for very long, so you can't really see what happens to the money. Like remember I showed you that graph where it turns and grows? You want to leave your money there for a long enough time where it really starts to grow into something. And to do that, it needs to stay there for at least 30 years. You know, some people are like, well, I don't want to leave my $5,000 sitting there for 30 years. I want to spend it. Okay, well then you don't get to make a lot of money from your investments. Remember I said you have to be patient. You have to be willing to leave your money there. So let's just say for 30 years and see what happens. All right, so that means I'm compounding monthly, which means 12 times a year. That's not continuously. So I need to use the first formula. So A is going to equal P times 1 plus R over N raised to the NT. So that's my $5,000 times 1 plus 8%, that's 0.08 divided by N, which is 12 times a year. What we're doing is we're taking that yearly interest rate of 8% and breaking it down into 12 equal interest payments. You don't get 8% every month, you get 8% for the year. So for 1 month you get 8% divided by 12. Raised to the 12 times 30. Okay? And so the reason we put that 12 in there is because we've changed this to a monthly interest rate, and there are 12 times 30 months in 30 years, 360 months. Okay, so now I'm going to take my calculator to figure this out. All right, so I'm going to punch in 5,000, times 1 plus 0.08 divided by 12. Now, if I wanted to, I could go through and figure out what this equals and then do 1 plus that, and I could have 1 point something, just a number in there. I could do that. But I'm just going to let the calculator do it for me. Okay, I don't really need to see what that number is. And then I'm going to raise that to the 360th power. There's what I get, 54,678. 54,678. Now, remember how I said we always round to 3 decimal places? Well, we don't do that with money. You know, money we only go 2 decimal places because that's our money system. So I need to round this off to 0.65. There's the amount of money that we would have. You know, so some people look at that and they go, that's not, I mean, yeah, $54,000 is a lot of money. But it's not like that much. I mean, I let my money sit there for 30 years. It's not that much. Okay, well, what if you did some homework and you found a place where you could invest money for 14%? Let's go back and change this. So I'm going to change my 0.08, I'm going to change that to 0.14. So I'm going to go second enter, it brings the whole thing back, and then I'll arrow up to here, and right there I'm going to go 1.4. How much of a difference did that make? Oh, okay, now we're talking. $325,423. 325, what was that? 423. 0.31. $54,325,000. That's a big difference. That's $275,000 difference, about. I'm just estimating. That's kind of a lot. Is it worth doing your homework to try and figure out how to get this percentage versus this one? I would think so. If somebody knows where to look, you guys can try this. You get on the internet and do a search for mutual funds. Find something called Fidelity Mutual Funds, and if you can go in there and find their list of funds, you'll see funds in there that pay like 30% because people are investing in the right thing. You know, pharmaceuticals, anything that has to do with medical supplies, good investment. You know, what if that number would have been 30%? How would that change this problem? Second enter. Let's go back and change this to 0.30. There's 30%. Ooh! $36 million. You know, the question that people always ask is, if this could really happen, why don't people do this? And I'm going to tell you, people do it. That's why we have billionaires. They know how to invest their money. Why doesn't everybody do it? Because we're impatient. Nobody wants to take their $5,000 and go let it sit there for 30 years. I want to spend it now. I'm not saying I do. I'm just saying that's what people generally think. That's a good down payment on a car. That's a new set, new living room furniture. Or a new bedroom set. Something like that. So, and do I even have $5,000 to begin with that I can afford to invest? That's the thing. If we don't have that, it's pretty difficult to make this happen. This is why people say the rich get richer, is because the rich people have money to invest. They can go and do this, and they know where to look to get that big interest rate. And the moment that mutual fund quits paying, then they sell it off and they go look for the next one, and they invest. Let's make 30% here. That's a lot of money right there. Okay? All right. I always thought this was interesting. Here's another problem. So let's see, this would be 5. Let's just say that, let's say I was a nice dad. And when my kids were born, I invested $1,000 each. I got 3 kids. Okay? I didn't really do this. But let's say I did. I'm going to invest $1,000 at, say I did my work, and my homework, and I went out and found a good investment. I think 14% is pretty good. Okay, I really do. I think finding 30% that'll pay year after year after year for 30 years is really hard to do. I'm not going to say it's not there, but you got to look awfully hard. You got to know what you're doing to find it. But let's say I could find something that pays 15%, and I'm pretty sure I could keep that going year after year. Okay, compounded continuously. Okay, because really when you invest in stocks and bonds, they're continuously changing. They're always going up and down. It's not just a set amount of money that they're worth. Okay, it's continuously changing. So 1,000% at 15% compounded continuously for 60 years. My goal was to give them $1,000 when they're born, and that'll become their retirement fund when they turn 60. Let's see what happens. So compounded continuously, that means I'm now using this formula. So that's $1,000 times E, remember it's just a number. My interest rate is 0.15 times 60 years. So the R and the T are both in the exponent. So I grabbed my calculator, 36 million, that was a lot of money. So I'm going to go 1,000 times E. Okay, right here where this ln button is, that's e to the x. So they put the exponent there and they start off with parentheses. I think on your calculator it'll put it up into the exponent. And then you just have to do 0.15 times 60. And then for me I got a close parenthesis. For you guys you just arrow to the right to get out of the exponent. And then you hit enter. Wow. $8,103,083.93. 08393. That'd be a pretty nice dad who would do that, right? And the key to this, 8 million, is 60 years. The longer time period you have, the more your investment has a chance to grow. You got that exponential growth and really take off. Okay? That's what's happening with this right here. And again, why don't people do this? Because people would rather spend $1,000 than invest it and wait 60 years for it to turn into something. I don't get it. I'm a pretty patient person. I don't need all that money right now. And you know, here's what most people do. Rather than investing $1,000, what people do is they say, you know what, when I get my paycheck, I'm going to pull $100 out and go and invest it. And I'll do 100 next month, and then the next month. And so what you end up with is a whole bunch of these investments where, one of them sat there, or, maybe you do it per year, like $500 every year. So one $500 sat there for 60 years, the next 500 was 59 years, the next one 58 years, and so on. And you can do the math, it'd take a while to do all that, but you can figure out what that's worth. It would be worth a lot. And so that's how people get around investing a large sum of money, is we just invest a little bit at a time. Okay, $100 out of every paycheck, it's not going to hurt anybody. $200 out of a paycheck, it's not going to hurt you that much. I would be willing to bet most people could once you have a career type job, you could handle investing $500 out of every paycheck, every month. Just if it's not there, I'm not used to it, so just let it go. And that way someday I can retire with money like that, where I can go play golf and go skiing and travel and have some fun. That's what the retirement years are really about. All right, one last problem. You guys go ahead and try this one. We're going to invest $7,500 at 12% compounded weekly for 18 years. All right, so it doesn't say continuously, so that means I'm using this formula. Okay, just write this down every time you use it. You'll have it memorized in no time. All right, so $7,500 times 1 plus 12%, 0.12, divided by weekly. There's 52 weeks in a year, right? So divided by 52, and then raise that to the 52 times 18. All right, so I'm going to put that in my calculator. I've got 7,500 times, in parentheses, 1 plus 0.12 divided by 52. I'll close parenthesis and then raise that to 52 times 18. I don't really know what that is. I guess I could have done that first, but I'll just do this. I'm going to go 52 times 18. I'm going to put it inside parentheses so we know that the calculator has to do that first, and then it becomes the exponent. So there it is, $64,871.90. There's my investment. 18 years isn't a huge amount of time in terms of investment. So yeah, it did grow a little bit. I mean, 7,500 to 64,000, that's significant. But that's not enough money to retire on. We need that to grow more. And so really the key to this problem is that number right there. That's the key. It needs to get big. That's why I say our book always asks kind of boring problems, because they use small numbers like 5 years, 8 years. It never amounts to that much money. It becomes interesting when you start talking about leaving money for a long period of time. All right, let me get you guys a homework assignment. All right, so here we go. This is assignment number 15. This is our Wednesday piece, page 227. We're going to do 45 to 61 odd, and then 65, 66, and 68. All right, you guys, that's it. That's all we have for today. You guys take care, stay safe, and I'll see you on either Thursday or Friday. All right, bye.